All right, you guys. So today we are going to be talking about gases. So the other day in lab, you got to explore just a bunch of different scenarios, right? And all I was asking you to do was take observations. What did you see? What did you feel? And what did you hear, right? Did things get hot? Did things get softer? Did things get bigger, smaller? Whatever, right? Did mass change? Was something difficult to do? Was something easy to do? That's what you were exploring. And all of those scenarios, all nine, I think, stations that you worked through, everything you experienced and witnessed was based on some of the behaviors of gases. And so what we're going to be looking at today is what some of those behaviors, these nature of gases, what do they stem from? How do they influence things around us? And what are the big relationships for those? Okay. So we did talk about gases a little bit last semester. We spent a little bit of time talking about the states of matter, and you watched that little video where they were soccer players, right? And they were running around versus in a huddle versus speeding down the field, spread out, or were they really close together? Were they moving? Were they not? And so that weird little soccer player video was an analogy about what the molecules do in the different states of matter. And so when we are talking about gases, we had the large scale characteristics. So like, what do we see with like our own eyes about gases compared to what's happening on the molecular level? So for that large scale characteristics, that's where we were talking about like volume and shape. So digging deep back into our memories. Okay, so when we're talking about gases, we said that they did not have a definite shape nor a definite volume, right? We could change those things regardless of what we were talking about. And then on the molecular level, you might remember me waving my hands around in front of you, where the gas molecules, right, they were going all over the place. Okay, so we said that on the molecular level, our gas molecules are spread out and they are moving rapidly. Okay, and so these characteristics, no definite volume, no definite shape, and the fact that the gas molecules are spread out and moving rapidly and constantly, right? Like they're constantly in motion. These factors are influencing the behaviors that we see for gases. So the first one here is that gases have mass. Often people don't think about it, right? Because if you just cup your hands together, you're not like, oh, this is so heavy. But remember, mass is anything that takes up space, okay? And so keeping that in mind, that difference between mass and weight, when I cup my hands together, there's something there. And when you pump up a basketball, or if you think about the lab where you had to literally hand pump air into that soda bottle 100 times, you should have noticed a difference in the scale. So when you're looking at this image here, you have the deflated basketball versus the inflated basketball. Okay, gases do truly have mass, even though we can't see them, even though they feel weightless to us, they do indeed have mass. And so that's one of the important concepts to keep in mind when we are talking about gas molecules, okay? Gases are compressible. So the word compressible, if you don't like that word, gases can be squished, okay? So if you squeeze a gas, you can change its volume. And so if you're looking at this on the Google Slides, that little image is moving up and down. And the reason for this, again, I want to drive back to what we talked about last semester about what's going on the molecular level, is that gas molecules are spread apart and that they're moving. And so if you think about it, if you have two gas molecules that are this far apart, well, you can continuously keep them together. So again, gases are spread apart and gases are moving. And so what this means, right, if these are my gas molecules, well, what's right here, right? Like what's between these gas molecules? Empty space. Okay, so between your gas molecules, you simply have empty space, and that is what allows them to get closer and closer and closer together. So again, the fact that they're spread apart What is between them is empty space, which means they can get closer and closer together, aka they are compressible. Okay, right? So compressible, we're talking about their squishability. All right. And so maybe you have even used a pump before, right? And you pump, 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 pump. It's super easy at the beginning. And then as you continue to pump, it gets harder and harder and harder. Well, you've compressed something as much as you can. You have filled that empty space. And so it gets tougher and tougher. So this example right here, what you see, that image, that is a piston. And so it's squishing, it's squishing, it's squishing, and the gas molecules, which are spread apart, get closer and closer and closer and closer together until they're truly too close. And so this actually goes back to that air duster canister. So with the air duster canister, what we were seeing there, if you remember how it's the bottle itself said don't shake, but the directions in your lab said to shake. When you shook it, hopefully you heard something, and what you were hearing was liquid, but when you sprayed the compressed air, certainly liquid didn't come out, right? All that came out was gas. That's because what's happening inside the can, the reason they're called compressed air, is because they've compressed those gas molecules so much that they are no longer spread apart. They're actually close together. And as such, they're actually in the phase of a liquid. So that's how those work. The other thing to keep in mind about gases is that they are going to fill their container. And so what we are talking about here is that gases will continue to expand and take up as much room as they possibly can. And so we sort of, when we think about this, the image that you're seeing here, right, like your solids, they're not moving, they're just in a corner. Liquids, they're simply slipping past each other, but gases are moving constantly. They're not going to just be moving in one corner of a room. Okay, that would totally inhibit our ability to even be breathing. The gas molecules are going to be filling the entire space that they are in that constant motion. They're not just going to overwhelmingly be in one part. They want to fill their container. They want to spread out. And so this fact that they want to spread out, that they want to fill these containers leads into the next nature of gases. Okay, so 3 and 4 really tie in together. 3 is saying that they want to fill their container. 4 is explaining how they do that. Okay, so that is that gases diffuse. So maybe you've ever, one of the most classic visual examples of diffusion is somebody adding like food coloring to a container. First, you can just like do a little drip and you can like see it's like very concentrated, whatever that color is. And then as that food coloring sort of spreads through the container, that is the example of diffusion, spreading from an area of high concentration to an area of low concentration. This is why those, if you've ever seen those little jars of liquid with the sticks coming out of them, they are called diffusers. Literally based on the principles of chemistry. They're called diffusers because the liquid sort of travels up those sticks and then evaporate as gas, and they diffuse through your space to make it smell good. This is the same reason why if someone lights a candle, you can smell it on the other side of the room. The candle itself is the high concentration. The other corner is a low concentration. And so those gas molecules that are evaporating from that candle are spreading out from the candle out, right? Like we always know when someone is someone is making popcorn at home or at school, right? Like we can smell it from so far away. And again, that is based on this high concentration to low concentration spread. This is going to definitely depend on size and energy. The heavier a gas molecule is, the harder it is for it to spread. And the lighter it is, the easier. So we know molar mass at this point. So like hydrogen gas, you're talking about 2 hydrogen molecules, that's about 2.016. Pretty zippy. Hydrogen can spread around pretty fast as compared to fluorine gas or chlorine gas. These are going to be much heavier molecules, so they diffuse slower. So the lighter something is, the quicker it diffuses. Same with energy. The more energy something has, the quicker it's going to diffuse. Okay? And then the last thing we want to keep in mind about the nature of gases is that they are going to exert pressure. They physically exert pressure. So the definition that we are going to use for pressure is that it is the sum of the collisions of gas molecules with their container and themselves. Okay. Again, that is the sum of the collisions of gas molecules with their container and with themselves. So literally, when somebody runs into you, right, you feel that. You feel the pressure exerted on you by another person. We aren't just like walking around being like, ow, ow, these gas molecules are hitting me. But that is actually what's happening. Gas molecules are exerting pressure on you at all times. And so those collisions of gas molecules are exerting pressure on you. Okay, so again, the big key word that you want to remember with the word pressure is collisions. Okay, so you hear pressure, think collisions. Hear pressure, think collisions. Okay. So just go ahead and take a beat and just list those 5 properties of gases in a row, just so you can kind of have that like resource for you as you are studying. Okay, so just go ahead and list those 5. Okay, so we're going to wrap up part 1 of the nature of gases here, and then we're going to move into part 2 now.